Okay, next week y'all have a 3-day weekend next weekend. Yeah, on Monday the 11th, it's what did I just look up? Columbus Day, I think. And y'all are off next week. I'm sorry. No, not a 4-day. Not a 4. Yeah, there, that works.
We're going to learn about what they are.
All right.
In this video, we're going to talk about the basics of molds.
I'm going to stop that for a minute. If you like, sometimes if I teach something and you're having a little trouble understanding it, this guy is really good and he's very easy to understand. He does a lot of chemistry videos.
We're going to learn about what they are, and we're going to talk about some of these important numbers and terms. Now, we're going to start at the very beginning on molds here. So no matter how much you know or how much you don't know about molds, this video will be a great place to start. So what's a mold? I'm not talking about the cute little furry creatures that live underground. I'm talking about the kind of molds that are super important. So a mold is a name for a specific number of things. Okay? A mold is kind of like a dozen, right? A dozen is the name for 12 things, or 12 things in a dozen. Now a mold is like this, but it's way bigger than a dozen. 12 things in a dozen. In a mold, there are 602 hexillion things. This is 602 followed by 21 zeros. 602 hexillion things. So a mole, like a dozen, is a name for a certain number of things. There are 12 things in a dozen. There are 602 hexillion things in a mole. This is a gigantic number. Now, here's one thing that confuses people about moles. They forget that a mole is a name for 602 hexillion things, and they think that a mole is an abbreviation for the word molecule. So many people think this. They see mole and they think, oh, you mean molecule. No, no, no. If I write mole, I don't mean molecule. I mean a group of 602 hexillion things, not a molecule. So there are 602 hexillion things in a mole. And just like a dozen, we can have a mole of anything, right? So we could have a dozen donuts, which would be 12 donuts. Or we could have a mole of donuts, which would be 602 hexillion donuts. Or hey, we could have jelly beans. A dozen jelly beans would be 12 jelly beans. And a mole of jelly beans would be 602 hexillion jelly beans. So sometimes people get freaked out about moles, but just remember, they're a lot like a dozen. 12 things in a dozen, 602 hexillion things in a bowl. You can have a bowl of donuts, you can have a bowl of jelly beans, a bowl of cards, a bowl of paper clips, a bowl of bouncy balls, just as long as it's 602 hexillion things, you got a mold. Now let's talk a little bit about this actual number, 602 hexillion. This number is often referred to as Avogadro's number in honor of the Italian scientist who discovered it. But now, check this out, right? 602 hexillion. This is a gigantic number. 602 with 21 zeros. Think about what a pain it is to deal with this number, right? If you're doing math by hand, you got to write this out, like do your multiplication and division with 21 zeros. Even if you're using a calculator, you got to type in all of these zeros, make sure you have the right amount, and then when you get your answer, you got to go back and count how many zeros your answer has. It's a total pain. So instead of writing out 602 hexillion with all these zeros every time we want to talk about moles, we tend to abbreviate this number. Now, as you may know, when we abbreviate numbers in math and science, we usually use a technique called scientific notation. And here's how we would abbreviate this number using scientific notation. Okay, I've got this big number, 602 hexillion. I find out where the decimal place would be. It would be right here. And now I move the decimal place until I have just one digit to the left of it. Okay, I count the number of spots. So here's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. And now this is my new spot because there is a 6, just one digit to the left of it. So I moved my decimal place 23 spots to the left. And that means that in scientific notation, I would rewrite this number as 6.02 times 10 to the 23rd. The 23 comes from the number of spots that I moved it to the left. So 6.02 times 10 to the 23rd is how we often abbreviate this gigantic number, 602 hexillion, when we want to write it out and use it, say, math problems. Now, this is a convenient way to write this gigantic number in scientific notation, but it's also a terrible way to write it, because this number, 6.02 times 10 to the 23rd, it looks terrifying, right? It's got this 10 with the exponent, 6.02 times this thing. It's like people see this number and they're like, oh my God, what do I even do in this? Relax. It's okay. 6.02 times 10 to the 23rd might look a little terrible, but just remember that it is an abbreviation for 602 hexillion. That it is an abbreviation for this very large number here. Every time you see 6.02 times 10 to the 23rd, just remember that it is an abbreviation for 602 hexillion. Okay, so now we've learned what a mole is, how many things are in a mole, and we've learned how we can abbreviate this gigantic number, 602 hexillion. The last thing I want to do is give you a sense of how gigantic this number, 602 hexillion, how gigantic it really is. Okay? So let's think about this bowl of jelly beans that we talked about earlier, 602 hexillion jelly beans, which you know now we can abbreviate as 6.02 times 10 to the 23rd jelly beans. These are all just three ways of writing the same number. Okay. If you had 602 hexillion jelly beans, that would be as large as the entire planet Earth. A mole of jelly beans would be as big as the planet Earth. That is crazy. Think about how many jelly beans. I mean, really, think about how many jelly beans it would be if your house were filled with jelly beans. Okay, that would be gigantic. Think about how many jelly beans would be if every building in your town was made only of jelly beans. Okay, like that would be a ton. Now, imagine how many jelly beans you'd have if the entire Earth were made of nothing but jelly beans. And that is how big a mole of something would be. Now, we could have also a mole of donuts, which would be 602 hexillion donuts, 6.02 times 10 to the 23rd donuts. If we had this many donuts and we stacked them on top of each other like this, we had 602 hexillion donuts, and we kept making the stack. This stack would reach from the Earth to the sun and back 200 billion times. This stack of donuts would reach from the Earth to the sun, back and forth 200 billion times. Again, think about how many donuts we would have if we just laid donuts down like this from like your house to your school, right? That would be a ton of donuts. Now imagine going from Earth to the sun and back 200 billion times. That is how many donuts 602 hexillion donuts is. But now here's the thing, this is really interesting. We're talking here about jelly beans and donuts, but a lot of times in chemistry, we're talking about things that are much smaller. We're talking about atoms. Now, a mole of jelly beans would be as big as the planet Earth, but a mole of atoms is much smaller. Here, in this container, I have just about 1 mole of sulfur atoms. This yellow powder, these yellow chips, are made entirely of sulfur atoms. And there are about 602 hexillion sulfur atoms in this little dish here. So think about this, right? Got 602 hexillion sulfur atoms right here. Now, 602 hexillion jelly beans would be the size of the planet Earth. 602 hexillion sulfur atoms can fit in this little dish. This shows us how absolutely tiny a sulfur atom is, how tiny all atoms are compared to a jelly bean. Really, a mole of these is the size of planet Earth, but a mole of these little sulfur atoms can fit in this dish. So when we're dealing with something as tiny as atoms, a mole doesn't actually take up that much space because the things that we're dealing with are so incredibly small. The giant number of them just isn't that big. So just to review what we've talked about, let's go over a few of the key things. So a mole is kind of like a dozen, except there are 12 things in a dozen and 602 hexillion things in a mole. We can write this number in a variety of ways. We can do 602 with 21 zeros after it. We can call it 602 hexillion, or most commonly, we can abbreviate this number in scientific notation as 6.02 times 10 to the 23rd. This number here, 602 hexillion, is often referred to as Avogadro's number. And now finally, at the very end of the lesson, we saw how 602 hexillion is a giant number. 602 hexillion jelly beans would be the size of planet Earth. But atoms are so tiny that a mole of atoms doesn't really take up that much space. So 602 hexillion sulfur atoms, for example, is a pretty manageable size. And that is an introduction to moles.
So we'll use moles throughout the whole year in chemistry. We use them for conversions and many other things. And there's even a mole day, which is October the 23rd. So next 6 weeks, probably on Monday, I'll tell y'all about a little, y'all can do a little project to earn 5 extra points on your second 6 weeks average. And it's going to be making a mole, even though there are different types of moles. All right, so let's talk a little bit more about that and how we're applying that today. So the mole can be abbreviated as MOL, but not just a little m, because that already stands for meters. And once again, just like atomic mass units, carbon 12 is your standard on this. So a mole is the amount of a substance that contains as many particles as there are atoms and exactly 12 grams of carbon. So if I massed out 12 grams of carbon and I was able to count every atom, I would have what would be called a mole of atoms. And that's true for any kind of particle that we use in chemistry. And some of those particles are atoms, molecules, ions, and formula units. Atoms are if we're talking just about a single element. Molecules are if we're talking about covalent compounds. Ions are if we're talking about an ionic compound that is just now in ions. And formula units are if we're talking about ionic compounds. So in other words, all of those are different types of particles, more specialized depending on whether they're part of a compound or whether they're all by themselves. And on Monday, what we're doing is a little bit harder than what we're doing today. And so this is a hint. If you see one of these particles, it tells you you're going to use Avogadro's number when you do your conversions. So that's kind of how they become important. So Avogadro's number is the number of particles in exactly 1 mole of a pure substance. And remember, a pure substance is either an element or a compound. And that number would be 6.02. You can take off one of your twos. We're just going to use it with 6.02 times 10 to the 23rd particles. And once again, that was if you could count them, which you cannot. So you can kind of think of it like a counting number, like a dozen or a pair. If I had a dozen golf balls or a dozen ping pong balls, I have 12 of each one, but the golf balls would be a lot heavier. Same thing, if I have Avogadro's number of hydrogen ions, which is element number 1, or Avogadro's number of uranium atoms, which is number 2, I would have 6.02 times 10 to the 23rd atoms of each, but the uranium would be a lot heavier because 1 atom of it is heavier. So to kind of wrap our mind around it, instead of continually using Avogadro's number over and over, we use something called molar mass or formula mass. And that's what we're going to be looking at today. So he kind of went over how large Avogadro's number is, just to kind of give you an idea. If every person living on Earth counted 1 mole of oranges, and each person counted at a rate of 1 orange per second, it would still take 4 million years for those oranges to be counted. So it's a huge number. And since the mole is so large, we use it to count very tiny things like atoms. We're not going to count Avogadro's number of cars. That would be huge, a huge mass. So instead, we apply it to very small things. And once again, since we know we can't actually count out that many things, it's going to be easier if we kind of convert that to mass and deal with mass and grams like we're more used to looking at. So the mass of 1 mole of a pure substance, whether it's an element or a compound, is going to be what we're looking at. And that's going to be the molar mass. And it's going to correspond to the atomic mass, which is on the periodic table. So the atomic mass is the mass of 1 atom of any element measured in AMUs. And because of the standard that was developed whenever the scientists first started doing that, that also happens to be the mass of 1 mole of atoms measured in grams. And we call that molar mass. So for instance, if I look at copper, and copper is element number 29, and I wanted to know the molar mass of just copper, I would simply get that straight off the periodic table. And I'm going to put element in parentheses, because once it becomes a compound, then we have to do a little bit more work. But if it's just a single element all by itself, and I needed its molar mass for some type of conversion, I could get that straight off the periodic table. So if you look at copper, which is element number 29, that 63.55 is its atomic mass in atomic mass units, and it's also its molar mass. So 63.55 grams per 1 mole. And that's what we call the molar mass. Molar mass is always so many grams per only 1 mole. So once again, if I could count out Avogadro's number of copper atoms, and I was able to take those over to the balance, it should have a mass of 63.55 grams. Now, if we have a compound, it requires a little bit more work, and that's what you should have kind of seen on the video and what we'll be looking at today. So if you want to find the molar mass of compounds, you have to think what elements are in the compounds and how many atoms of each element are in there. And then you would take into account their mass off the periodic table. So first of all, you need the correct formula. Eventually, you'll have to learn how to write those. Right now, I'd be giving you the formula. You look up the atomic mass of each element, and then you multiply that atomic mass by the subscripts, or how many atoms you have of each element. And then the last thing you do is add them all together. So if we just look at a really simple one, I'm going to do table salt sodium chloride. Every time, excuse me, every time you have a capital letter, that's when you have a new element. So in this case, I only have 2 elements. I have sodium and I have chlorine. And I kind of just set myself up a little system. Your system may not look exactly like mine. So those are my elements. And then I look at how many atoms I have of each. Since neither one has a subscript, that means I just have 1 atom of each. And then I'm going to multiply that by their atomic mass off the periodic table. So if you look at your green sheet, sodium is element number 11. It's a group 1 metal. So I'm going to take its mass and round it 2 places past the decimal. So that would become 22.99. And then I'm gonna do the same thing for chlorine, which is element number 17. It's a halogen. So whenever I round its atomic mass 2 places past the decimal, it would become 35.45. I'm going to multiply through. In this case, I only have one of each. So 21.99, 35.45. And then I add those two together. And that's where we're going to get our 58.44 grams per mole. Once again, that means that there are 58.44 grams in 1 mole of sodium chloride, if I could count that out. When you're getting your number off the periodic table, you're going to round 2 places past the decimal. That's our rule in our class. When you go to college, your professor might have a little bit different rule, but 2 places past the decimal. So really kind of what I see whenever I teach molar mass is people don't really make the mistake on, figuring out the elements or how many atoms. The mistake seems to be in rounding. So that's what you'll want to do a little bit of practice on. All right, let's look at another couple of ones. We'll skip a little bit and look at some that are not complete. All right, so I think this is right below here. It says find the molar mass of ammonium sulfate. So there is my compound. So first thing I'm going to do, I'm going to identify my elements. I have 3 capital letters, so that means I have 3 elements. So I have nitrogen, hydrogen, sulfur, and oxygen. And now we need to put how many atoms we have of each. So that's kind of why I did that little video and the little counting review. So for nitrogen, how many atoms do I have? 2. Hydrogen, 8. 4 times 2 gives me 8. Sulfur, just 1. And oxygen, 4. All right, now I'm going to multiply that by their atomic mass off the periodic table. So nitrogen is element number 7. So how would that be rounded 2 places behind the decimal? 14.01, exactly. Hydrogen is element number 1. So how would you round its atomic mass 2 places behind the decimal? 1.01. Since that second 0 has a 7 behind it, it would come up to 1. Sulfur, element number 16. Perfect. And last, oxygen is element number 8. $16, exactly. Because you have 15.999. So once you start rounding and they go straight to 16. And things like hydrogen and oxygen, you'll get kind of where you memorize those because we use them so much. So now I'm going to multiply across. So 2 times 14.01 would give me 28.02. 8 times 1.01, 8.08. 1 would just give me my 32.07. And then last for my oxygen, 4 times 16 would give me my 64. So now I've taken into account what elements, how many atoms of each, and now I just add those up. And when you do, a couple of classes have checked my numbers, 132.17 grams per mole. And that's going to be the molar mass of that compound. So like I said, it's pretty easy. It's just a process. And like I said, the rounding is probably the most common thing. All right, why don't y'all try the next one? Has the chlorine and the oxygen in it. See what you get for its molar mass. All right, what'd y'all get on that one? 0.90, right? 182.90, yes, grams per mole. And I just tacked on that 0 so it would have the 2 places behind the decimal. Okay, so that is what y'all's practice is on. Y'all got a little bit of time to try a few of them. Answers are in parentheses right there. And like I said, the rounding is probably the thing that people tend to make the mistake on the most. So we'll have this quiz on Monday. You should do some practice at home tomorrow. So if you have any questions, you'll have time to ask that during our 20 minutes or so that we're together.